All right. Good morning, folks in US. Good afternoon in Europe. Good evening in India. Welcome to our second webinar from Movimento. Today's webinar is going to be about protecting autonomous vehicle and connected services with software-defined perimeter. We couple of just housekeeping. We have live chat, so feel free to ask any questions. What we will do is we'll go through the webinar, and then I'm going to take some of this live chat questions and ask our guest here, whom I will introduce shortly. This is a series of webinars. We are coming off from the last webinar, which was around monetization of software-defined car, and that's a very interesting one for folks if you want to know about what is software-defined car means and how to monetize from software and data services. So when we talk about data and software services, of course, the first and foremost thing that comes to everybody's mind is data security, data privacy, and in general the safety of the people and the vehicle. So with me, I have here Junaid. Junaid Islam is a cybersecurity expert. He is also the founder and president of Vidder. Vidder provides next generation cybersecurity solution, and the solution is a native cloud cybersecurity solution, and he brings those knowledge from being used in telcos, in enterprises, and now looking into industrial IoT. And Junaid and Movimento, or Vidder and Movimento, has been working on creating the next generation cybersecurity architecture for software updates. So with just a quick introduction here, you all know me probably. I'm Mahbubul. I'm CTO and CMO of Movimento, a Delphi company. Movimento provides software update and data management for automotive and to the industrial IoT. And I gave a quick introduction of Junaid, and Junaid is cybersecurity expert, very well known in the law enforcement in the government agency. That's all I can say. I don't want to go beyond that. Let Junaid do the talking soon. So let me just start with the agenda of what are we going to talk about. So continuing from the last webinar, I want to just refresh everybody into very quickly what are the industry trends and the direction towards data services. And then from there, we're going to talk about cyber attack vectors, and then the risk and threats that are there. Then Junaid is going to touch upon a concept of secure enclave design, and then software-defined perimeter, and then some key takeaways, and we'll open up for Q&A. So with this, I just want to go very quickly into this past, present, and future. It's very, very important we all know the past, we know what's today, but the future is what's very exciting and interesting. And I'm just going to highlight some of the things that are probably obvious to everybody, but just to see how far we have come and where we are heading. So we're looking 15 years behind and into the 2030, 15 years ahead. Actually, it's less than 15 years now. Mm-hmm. So just 12 years.
Time passes.
Yeah. So if you look at from the transistors point of view, the amount of electronics that went into the vehicle, you can see by 2030 we're talking about quantum transistors. The footprint of transistors are not are not small enough to fit into the electronic sizes that we are putting in. So and it's massive. In terms of the software and the software feature functionality, we are already in hundreds of millions of codes today in today's vehicle. Just to give in comparison to Boeing 787, it's about 6-7 million lines of code. So already factor 10x more in today's automotive vehicle. Think about autonomous vehicle. Think about the self-driving car. It's going to be billions lines of code. If you think about how the vehicles have been diagnostics have been done, we come from manual or diagnostics we took to the dealer. These days you just take your vehicle, they put in your key fob, and they get all the diagnostics, to moving to more of the self-diagnostics, where probably machine learning algorithms will come into play and self-diagnose themselves. If you look from the connectivity point of view, yes, we are having some connectivity. Gartner projects that by 2020, already 250 million vehicles will be connected. Almost all the vehicles that are coming out in the high end are getting connected, and that's getting proliferated to the mid-range and low end of the vehicle. But by 2030, there's no doubt about it, everything will be connected. If you look at in terms of the applications that we have, yes, we used to have simple, radio system. Then we went into today's, we have some media and some, connected radio services and so on, and with some limited apps. But what we're looking for is truly a connected services of all sorts of services, whether it is about local ads or restaurant attracting you, or insurance company, or parking. I mean, there are going to be plethoras of services that's going to come to the car, and so that's an exciting era. Next is in terms of our interactions with the vehicle. We have a basic interaction. We push few buttons to getting more of this virtual assistants. You have seen already Alexa's and so on. Not only has penetrated in your living room, but also into your vehicle, to more of the cybernetic, where human and AI are going to interact, and it's going to be all about your gestures and all those sort of things. It's going to be all very natural, very little of pushing the button or taking your eyes off the road, or even concentrating on something. Even if it is autonomous vehicle, you should be able to do something else and be more seamless between the machine and the human. Then the last but not least is all this brings it to the fact that security, right? Cybersecurity, from a world of not connected, no worry about security, to some connectivity and some security threats that we have seen in the last couple of years for the automotive. And what we're seeing in the industry is there's a lot of cyber threats, and it's really exploding in terms of amount of threats that are there. So what kind of solution we would look for 2030 is a default cybersecurity. It's just going to be part of our nature. It's how we go about. So this is why we are talking about is how do we prepare ourselves for 2030. So key thing over there is the software is exploding, and the connectivity is going to be intrinsic. It's going to be hyper connected, and AI and human interaction is going to be there, and the cybersecurity has to be default. Point. So how is the industry going about this data services that connected services means a lot of software and services? So how the industry is evolving? If you look at it, really take a step back, there are three business models that are prevailing in the automotive industry, and I will talk about those. The first one we call the basically data broker business model, and I will talk about in this slide what it means. But there is also another called data bartering, which is basically a data exchange to improve services. We'll talk about that. And the third one is more of the business intelligence, or more data as a service. So if you look at this one, this is a data broker business model, and really there are 5 key stakes. This is a value chain from left to right. If you can think about it, you got the vehicle, and then there are folks, in this case, Delphi Aptiv, where Control Tech and Movimento are part of those. We are helping to collect those data from the vehicle and smartly collect it and transport it to a platform. So the platform is a place of aggregation. This is where data gets aggregated. We make some decisions whether we want to do a software update or security patch or new feature functionality, but that's the data aggregation. Once the data aggregation happens, you give it to a data broker, and the data broker is basically anonymizing the data and finding a marketplace, creating a marketplace where people, whether they are from retail or from stores or from automotive or dealership or car sharing or rental, they can use those data to provide amazing value-added services that goes back to the platform back into the car. So this is a closed loop architecture. This is what is known as the data broker model. This is where Delphi with our partner Autonomo we are leading in the industry. There's also a data battering model where basically the similar thing exists, but what happens is you collect the data basically and you bring it to the aggregator, which is the platform, and then what it does, over there you anonymize and then create the value with the services, and you give back some of the value to the end user. This is what you see, for example, with Waze and city municipality, where basically Waze is providing some value of the traffic and city is providing some other value, and it helps improve both the services. So there's the exchange of information to improve each other's services. But the other interesting emerging is the business intelligence model, which is data as a service, and that is where basically you see that the platform would be a neutral player. So you would collect the data and you would give to the platform. User would have a consent whether they want to share their data for some services or not, and that neutral platform broker or platform vendor would then anonymize and provide a whole marketplace, and the user data, who is the owner of the car, can decide who their data should get in the marketplace for what services. And a good example of that is BMW. They have connected data services, where the neutral vendor for data aggregation and creating that place is IBM using their Bluemix. And that is also a very interesting model where the end user whose data is being collected and being used has a say in terms of who gets to use their data and how they get to monetize it. This is all great. The services and all those things are great, but there is fundamentally the question of security. And we know whether anything that's get connected, whether it is your home, whether it's your IoT device, whether it's car, security is the number one deterring factor for all these services. And people are really worried about their privacy, their data, and as well as the thought of your vehicle getting hacked, right, or hijacked. So this is where this webinar is going to focus on, is really the fact what I just explained in the last thing, is all the services that are going to come from marketplaces are going to be from all different people. They're going to get aggregated to a platform, and the platform is going to provide these services. So what you see on the left is a car with all this different color highlighting different sorts of services. It could be retail services, it could be dealership services, it could be map services, all sorts of services. But on the right hand side you have all these different applications of different vendors, and behind them there might be another set of services that are providing e-commerce services, telematics services, machine learning, improving. So you got all these different stakeholders with the different services and all those coming over there. How do you create a security, end-to-end security from the application all the way to the application in the car to the application in the cloud? So with me I have Junaid here again, and he is expert in cybersecurity and creating this cloud-native application and security end-to-end. So Junaid, why don't you walk us through this complexity, and how do you see this industry evolving, and what are some of the solutions?
Well, great. First, thanks for having me on your show here. And thanks for those people joining. Thing I wanted to stress for the people watching right now, this is a live webinar chat. So as you come up with questions, feel free to type them on the screen. And at the end of this session, we've set aside some time to answer questions. So please take advantage of that. So as Mahbubul showed in the previous slides, the connected ecosystem is actually key to monetization. There are services that the car companies want to offer natively, as well as a lot of services coming through partners. And more importantly, the goal is to give consumers choice. This is all actually very exciting, but from a cybersecurity perspective, what's happening is it's adding a lot of complexity. If you're looking at the slide on the screen, what we have is a lot of processes in the vehicle connecting to a lot of processes in the cloud, as it were. the challenge is it's not just processes in the cloud. A lot of these processes themselves are actually a collection of many applications, including partner applications. For example, there's some aspect of machine learning showing up in almost every aspect of the car. There's some aspect of telematics, showing up. There's e-commerce showing up. So we basically have a lot of complexity going on. So part of the challenge is the existing security model is really to say, let's build a super secure pipe between the vehicle and the cloud, and then let's make that work. The problem is it's actually very hard to maintain that level of state. I mean, there's a couple of ideas, and unfortunately we won't have time in this webinar to go into the ideas in a lot of detail, but we're going to focus on the risks. But there's people who are talking about using IPv6 addressing. The challenge with v6 addressing is mapping the v6 addresses of the processes to the v6 addresses of the vehicles. Then there's application layer gateway. Then we have a problem of matching URLs between the two domains. So a lot of high complexity and a lot of risk, but we're going to talk about how to take care of both of those. So looking at this at the next level of detail, the connected ecosystem really has three challenges that we need to solve and get right. The first one is the notion of multiple identities and entitlements both inside the vehicle and outside the vehicle. And what that means is different software partners are bringing in different processes with names or some identities, either URLs or v6 addresses, right? And these have to get authenticated and authorized in both directions, right? So we have processes in the cloud connecting to the car. We have processes in the car connecting to the cloud. We have to get it straight on who is, who's supposed to do this and not. The other thing, as I mentioned, adding to the complexity, is we have back-end partners like, let me use a simple example of machine learning. They might be going through a front-end application into the vehicle. Well, this is even harder because now this is someone else's process, basically slipstreaming behind your process. And what happens is with all of this highly connected ecosystem, we now have a set of attack vectors that we have to watch out for. So let me just kind of walk through some basic ones. So one of the most basic ones is credential theft.
Right.
Stealing the password of the, not just the driver, but imagine a global supply chain where you have downstream partners who are doing software. Maybe it's stealing the password of an engineer working 10,000 miles away. So we have to look at credential theft. We have to look at DNS spoofing, where a lot of these processes are using DNS addressing within the cloud or within the car to resolve to a server. We have to look at server exploitation. So this is where a cyber attacker can find a server, whether it's in the vehicle or in the cloud, and basically do a front door attack. Another attack vector is location spoofing, and that's where the hacker tries to either jam GPS or confuse the car, make it think it's somewhere else. Next, we have lateral moving malware. This is actually really becoming a problem worldwide. A few months ago, there was an attack in Ukraine called NotPetya, and basically this was a malware that had the ability to move by itself. It basically had a scanner built into it, and this is quite risky if you think about the connected ecosystem. You could imagine malware kind of moving from process to process in the cloud, moving to the car. I know. And then finally, we have OTA retasking. So this would be an example where the cyber attacker intercepts the link, tries to pretend to be a back-end process and actually send commands to the vehicle. So these are kind of the attack vectors. And now let's look at some of the potential outcomes. And I've grouped these in two blocks. So the first block is data theft, and there's a lot of privacy laws around that that we have to watch out for. The next is poor operation. So you could have a number of these attacks, and they might just not make the vehicle work properly. Next up from poor operation would be non-operation. That is, the vehicle is basically confused. As you know, autonomous vehicles have a lot of safety triggers.
Right.
And imagine the hacker just triggering one of the safety mechanisms and causing the car to just park itself, right? So while these are kind of risky, the next set is even more risky. So one of the interesting ones is vehicle theft. As you mentioned, I do work with law enforcement here in the United States, and one of their things they've thought about is someone just telling the vehicle to go somewhere else. So you wake up in the morning and your car is gone. So I know it's we're laughing now, but there's actually people worried about this. Next up, in terms of severity, is really hijacking the driver. So we're all familiar with ransomware, where you get malware on your computer and you have to pay some money, or it takes your data. You could think of a nightmare scenario where you're in the car and you get a text message that says, hey, if you don't give me some money, we're not getting out of the car. And then finally is the risk of terrorism. This is actually quite serious, and there's a lot of effort within the U.S. intelligence community and law enforcement to make sure this does not happen. And so part of the thing is, as an industry, we have to make sure the car is completely locked down, so
right.
None of these happen. So in terms of some of the challenges which are unique to cybersecurity, as you mentioned, I do work for large corporations, which is pretty complex, but automotive is even more complex for a number of reasons. First, autonomous vehicles are completely new. They're new on multiple dimensions, and they will be in a state of constant upgrades. I mean, that's just a reality.
Right.
This idea of changing the vehicle software is completely new for the industry, and I think it's just something we're going to be seeing a lot of, right? The next thing is new types of applications. You talked about innovation, and one of the ideas you brought up was the notion that users themselves will be making decisions, maybe doing car sharing, maybe turning their car into something that makes money for them.
Right.
Well, this adds a lot of complexity, because imagine you have an autonomous vehicle, but now when you're not using it, you actually give it to somebody else to use, and then they add their personalization, or they start tasking the car and saying, oh, come pick me up at the shopping mall, right? And off goes your car. So this adds to the complexity. And then finally, the global supply chain. The automotive industry is unique in the sense that it truly is global. We have buyers worldwide, we have manufacturers worldwide, supply the parts is worldwide, and now the software is worldwide, and this is all coming together for autonomous vehicles. So this is definitely a high complexity system. So as we think about cybersecurity, we need to be able to address all of these issues, the technical, the logistical, the business ones. So the model I'd like to talk about today and introduce is this notion of a secure enclave. So the secure enclave is actually not a new idea. When you think about the financial systems, like your ATM systems, when you think about online transactions, when you think about government networks, these are all examples of secure enclaves. And what the secure enclave really is a self-contained world. Where it has its own routing, DNS, own encryption. So it's a very easy to understand and well-proven security model, because basically all of the components you need for connectivity exist inside the enclave. So for applying this model to automotive, what we don't want to do is just have one enclave, right, where everybody fits in, because as we discussed, this is where there's a high risk of cyber attack. Imagine one of the 20 people creating software gets malware and it spreads through all of the other applications, right? So what we want to do is come up with an enclave model where we have a secure process in the vehicle connected to a secure process on a cloud over a dedicated application layer encrypted infrastructure. So very simplistically, one of the things people have talked about, including Delphi, is they're expecting almost 100 independent software systems in the vehicle. Mapping, infotainment, imaging. So imagine for each of those processes, we have a completely independent network, a secure enclave that connects that process to one or more cloud processes. And what this means is, if we have a breach in one, the breach does not spill into the other ones. What's also nice about it is because these networks are different, we can have different entitlements, we can have different digital certificates, we can even have different IP addressing, we can use any combination of v4 or v6 addressing. We can also make them short-term. For example, one of the things you talked about is maybe adding a new application, letting the driver wants to test something like a performance app,
Right.
Maybe that would now go into a secure enclave just by itself and wouldn't really interrupt the other applications. So using a secure enclave security model is definitely the right way to do it. It's proven, and it's actually very easy to understand. So the question becomes, well, this is great. There's a lot of secure enclave gives us partitioning, but how do we set up so many different secure connections between processes in the vehicle and processes in the cloud? I mean, this seems kind of hard. Well, this is where software-defined perimeter comes in. Software-defined perimeter basically is a way that we can provision dozens or hundreds of connections per vehicle for millions of vehicles. So it's very scalable and very elegant way to do this very complex mapping. So a couple of things about software-defined perimeter. It's a control channel-based architecture, and in the next slide we'll show you how the control channel works. So basically, through the control channel, it does something called attribute-based access control. And what that means is, instead of giving every process in the vehicle full access to the cloud or vice versa, it actually looks at what the entitlements are and then provides very fine-grained, very precise connectivity between the two sides. Another important thing, which is important for automotive, it does software attestation and federated identity. So let me explain that. There's a high risk with so much software coming into the vehicle that there's either malware or it gets tampered. Or maybe the tampering happened even before it showed up. So one of the great things about having a control channel architecture is you can remotely connect to the car and inspect it before it connects to a backend process. So this is actually quite useful. What you don't want to do is just connect the vehicle and then the malware or the attack ripples through. You want to be able to verify. Another important aspect of software-defined perimeter is it's basically got edge-based forwarding or routing. And what that means is, as we have different processes in the vehicle, we want to take them to a very specific cloud. So we can actually enforce that kind of forwarding at the edge versus backcalling, imagine 100 different applications to a point and then trying to distribute it. That is very complex, right? So we want to do as much processing at the edge, at the vehicle, versus trying to do all the routing in the cloud. That's not going to work. And two more things. SDP is multi-protocol based, and that's important because these processes, whether it's imaging or mapping, they have their own languages, and SDP is able to basically support the secure connectivity, all of them. And finally, it supports v4 and v6 addressing. So one of the great things about SDP is it's a layer 4 protocol. So it's application layer encryption, but that application layer encryption can exist on v4 or v6 or both, and supports v64 NAT. And this is a very important requirement for automotive, certainly for automotive in Asia. Asia is already v6 based, and here in the United States we're going to start seeing v6 connectivity quite a bit. So let's just see how this works together. So this is the picture we had earlier. We've got a car with a large number of processes, and then we have some back-end processes, front and back, and then So what we do is we have an SDP client in the vehicle, and we also have an SDP gateway. And think of the SDP gateway as your dynamically provisioned VPN firewall gateway and NAT. And then we have an SDP controller. So the first thing that happens is when the vehicle powers up, it sets up a secure channel, a mutual TLS-based, certificate-based channel between the vehicle and the controller. At that point, we run two sets of back-end processes. First, we do hardware identity verification. So that is, we match the hardware systems inside the vehicle to the digital certificate given. And we do that through the SDP control channel. We can also do things such as inventory management. The cars are so complex now that there is a requirement to do constant inventory of what's in there. The next thing, even more important than hardware, or once we've done hardware, is software attestation. So this is where we can remotely scan for what are the active software processes running, number one. The other thing we can do is we can do hash verification. So because we know the hashes of the software that went into the vehicle, we can now check the hashes to see if they've been tampered. And we'd probably be communicating with the cryptographic components of the cars themselves. So this is probably for another show, but the good thing is the chips, whether it's from Intel or Qualcomm, have a lot of native cryptographic functions that allow us to basically do the hash and make sure the hashes aren't tampered. So once the hardware identity has been verified and the software has been checked, then we go to the next step, which is look at the service plan. What has the user purchased, the driver, what packages has the OEM turned on. And then we look at those entitlements, and then we basically set up a secure data channel from the SDP client to the SDP gateway for the processes. Now, in this slide, if you're looking at the slide, I've set up one connection. But the beauty of SDP is really that we can set up an arbitrary set of connections. The great thing about SDP is it is a software construct.
Right.
So we can set up one connection, we can set up 10, we can set up 100. It really doesn't matter because we're using the control channel to basically say, well, hey, use software process, you've been authorized and authenticated to connect to this cloud process, and let me basically set that up for you. So it's a very elegant and scalable model. So the other thing I want to stress is, in the slide I just showed one SDP controller. The SDP controllers themselves are stateless entities. So you can have 20 SDP controllers, you can have 100 SDP controllers. So you could imagine 1 million cars connecting to controllers around the world. Then from there connecting to back-end identity and attestation systems, connecting to federated identity systems, and then basically these networks being provisioned. So it's a very scalable, elegant model. So the great thing about the secure enclave idea and using SDP as the architecture to implement it is it really allows us to do, I think what you talked about in your first webinar, is really a secure closed loop architecture, which is really where the automotive industry is going. They basically want to leverage the internet for connectivity. They want to leverage all of the great software in public clouds, but they need it to be partitioned from the broader internet, right? From a security perspective, a privacy perspective, a monetization perspective. So using SDP as a way to create secure enclaves really allows us to do this at tremendous scale. So that's very nice. So just wrapping up here, and then we've got some Q&A questions that some people already sent. So some key takeaways is that the connected ecosystem is really foundational to the future of the autonomous vehicle and actually even connected car in terms of safety, navigation, performance, telematics, entertainment, the whole list. Next, because we are so connected, there are multiple cyber attack vectors that have to be mitigated. Fortunately, we have a secure enclave model, which is kind of ideal. It's very easy to understand. It basically says we're going to partition all connectivity from a software process in the vehicle to a cloud process over a dedicated connection. And what we find is SDP is an ideal and very elegant way to do that. Then finally, we pulled this all together and we were able to create, moving back at the 100th industry level, this really allows us to create a closed loop architecture that is what the automotive industry wants to do in terms of monetization. And so with that, I guess you have some questions?
Well, I encourage, thank you, Junaid, first of all. A great intro to SDP and the concept of enclaves within the automotive. I encourage the viewers to, use the live chat to ask questions. I have some basic. I'll just start and with few questions, and hopefully people will text more as they see the interest. One key thing is you talked about SDP, right, and its ability to scale. So, can you talk about how scalable is SDP, and in that, what is the role of Vidder in that?
Sure. So software-defined perimeter is very scalable in the sense that it is control channel based. In very simplistic terms, if you had an enterprise, you can have an IT person basically run around and configure 100 laptops, and you have certainly Fortune 500s who have large teams who basically use, for example, Microsoft GPO policies to manage large pools of laptops. But when you get to hundreds of thousands of cars or millions of cars, being able to directly provision is just way too complex. So the fact that SDP uses a control channel, which doesn't change, to allow you to make provision changes is actually a very nice, elegant approach. In fact, it is the only approach, because you're not going to be able to manually connect to vehicles and then reconfigure them or reflash them or ask someone to come back to the garage.
Right.
That's not going to work for autonomous vehicles or connected cars. The other thing is the other idea we've seen in automotive is basically pre-configured secure connection. That actually works fine for demos or pilots. A lot of the connected cars we're seeing today have a lockdown connection. But if you think about all of the new services people are going to bring into the cloud, it doesn't work because the clouds themselves are changing, the application partners are changing. So again, using the control channel to be able to provision or rehome connectivity is really key. So one of the nice things about SDP is the fact that we can set up so many secure connections. And a great example of someone who's already working in this area and has done a lot of work is actually Verizon. Verizon this year in June did something called Operation Convergent Response, where they set up secure enclaves using SDP on their wireless LTE network, and basically showed that their wireless footprint is gigantic, but they showed that they can create an arbitrary number of secure enclaves on top of high-speed wireless, and that all of these could mitigate or could successfully stop all of the attacks we kind of showed. So I think that there's already a lot of work being done with building scalable, secure networks, and I think probably what we're trying to do today is bring those new ideas into the automotive world.
And Vidder's role is?
So we do two things. Yeah, thank you for asking that. So we develop SDP software, and we basically have two go-to-markets. The first one is we provide enterprises with secure enclaves to protect highly sensitive applications in the cloud. So, for example, we're working with a bank, and they have regulated FFIEC and data, and they're able to run in a public cloud because the secure enclave Vidder creates makes sure that nobody except banking people can get to it. More importantly, there's no way to know that the bank even runs in the cloud. So that's the enterprise side, and we also have other customers. We do everything from protect intellectual property, chip designs, formulas for famous drinks and stuff. Another part of our business is we actually also supply SDP software to solution partners. So an example of that is what we do with Verizon.
Right.
And now, I guess what we're starting to do with Movimento, where we provide our technology as a part of someone else's broader solution.
Excellent. I see a great question. I had some other questions, but this is very interesting. I think it's a very hot topic, and it's from Ritesh. And his question is it feasible or possible to implement blockchain-based architecture for in-vehicle software to ensure better security? And can you shed some light on the potential of blockchain to improve security? So just to add to that, is blockchain an alternative to SDP, or is blockchain, if blockchain is something, it will be good to hear. And if it is it better than SDP, or is there some relationship? Can you talk about, I know blockchain is not a topic we talked today. Look for this article that is coming out, I think this month, where Junaid and I have written an article around combining SDP and blockchain, but maybe you can talk about it.
Well, I'm happy people are taking advantage of the live chat. So I think blockchain and SDP are actually very complementary. For those of you who know, blockchain allows very scalable, secure messaging. So there's two applications of blockchain relative to SDP. One is, think of SDP as very secure connectivity, which is provisioned using digital certificates. And now think of blockchain as secure messages. So you can imagine with the SDP control channel being set up, that software processes within the vehicle use blockchain to send status messages to back-end processes. And then when a persistent connectivity is required, then through the control channel, we set up a longer time message. So a great example, just to use a similar, is cars have imaging cameras, and one of the ideas is if the car gets confused, say there's snow, a lot of the OEMs are thinking they want to backhaul all of the imaging from the car just for emergencies, or if the car's computers are confused. Now, we don't want to do that for every car because the amount of bandwidth is massive, right? But what we find is the combination of blockchain and SDP is quite elegant. You could have blockchain messages, very short and secure, coming from all of the vehicles back to the OEM on the status of their imaging solution. And for the few cars that are generating alarms, because I use snow because snow is very difficult, because sometimes you have to drive around and the road is white. But for the few cars that are, maybe the onboard systems are confused because there's a complete whiteout, it says, then the cloud says, okay, give me all of your imaging. It then sets up an SDP connection to a cloud to basically backhaul all imaging and sensor information to help the car understand where it is. So I just used that example of one of many, but I see blockchain and SDP as being very complementary and actually foundational. And if there's interest in this topic of blockchain with SDP, we could certainly have a drill down on that.
Absolutely, and look for our joint article that's coming out end of this month or sometime this month. I know we're going into lot of advanced topics, and I think for most of the listeners could be very interesting to dial back and take a step back and say, what's wrong with your VPN today? We have VPN solution, IPsec VPN, we have SSL VPN, we log in and we do banking. Why do we need something different for car? And what are the things that we are overseeing that SDP would be able to come and address?
Yeah, so there's two kinds of VPNs we're most familiar with from a consumer perspective. One is SSL VPN, which is the browser-based approach. So when you sign into a bank, typically you're thinking about SSL. The problem with SSL VPN is it's credential-based and it uses DNS to resolve or find the server. That does not work for automotive, just because it's not scalable enough. And of course, you're open to DNS hacking and connection hijacking. The other kind of VPN is IPsec, which is what we use for companies. IPsec is actually very secure. Unfortunately, it's not very scalable because IPsec goes from the vehicle to a specific gateway. And if you use IPsec, what would happen is you'd have to, once you got all the application data, you'd have to route it to a different cloud. If you look at a lot of the autonomous driving demos and tests, they all use IPsec now. So it's actually, the scale, it is very secure. The scale is though fine for demos and 100 cars or 1,000 cars. It's not going to work for 1 million cars. So at the level of 1 million cars, what we want to do is be able to route flows from within the vehicle to their destination, which is where SDP comes in.
And probably also the concept of end-to-end security and data integrity, because if you're terminating at the VPN gateway in the cloud and then you are setting up another VPN to some other cloud behind, you have a place of vulnerability where something could happen, right?
That's right. So an important idea in the secure enclave concept is actually software process in the vehicle to software process in the cloud. So there's been a lot of great activity in in-vehicle security at places like Delphi, and we actually want to leverage the fantastic in-vehicle security by connecting it to the great cloud security. So there's been a lot of great cloud security, both at Amazon and Azure. So what we want to do is to say, okay, we want to take this very secure process in the vehicle and directly connect it to this very secure process in the cloud. More importantly, we want that connectivity not to be shared. We want to be able to go from process to process. So that's the heart of the model. And you might say, well, does that stop all cyber attacks? The answer is no, but it makes first the cyber attacks very difficult, number one. But number two, if there's a failure or breach in one of the pathways, it doesn't affect the other ones. So we want to make it either difficult or impossible for attackers to completely hijack a vehicle. So if you can think about multiple safety systems in the vehicle, we want them to be in completely separate enclaves, forcing the attacker to play their heart.
So I see some more great questions. So one is from gentleman Leo Dumov. So his question is, could you please elaborate more on how SDP operates in a closed loop architecture in this case after the initial check over control channel? Does it monitor only a vehicle or also the services?
Yeah, so thanks, that's a great question. So the control channel itself is a mutual TLS connection, and the idea is that mutual TLS connection is used for what you would consider back-end or infrastructure services just for connectivity. So for example, when the vehicle first powers up, we can use the control channel to look inside the vehicle to see what's the hardware inventory, what chips do I have, what's the software, can I check the hashes. Then after it looks at the identity of the driver and what packages, and it sets up those connections, the control channel actually can keep running. So it's not like the control channel disappears. You can use the control channel to basically keep monitoring the software processes in the vehicle to make sure they behave well. You might, just thinking out loud, you might have a process that's using a lot of memory and pushing against some other processes, right? So the control channel is basically the way the OEM is able to keep monitoring not just the software process they put in the vehicle, but the partners. So you could have a partner who's focused on machine learning, who's uploading data. Right. You might want to make sure that they're only uploading at a certain pace. I use that as a simple example, right? Or say you have someone who's a car sharing. You want to make sure when they are sending their tasking orders to the vehicle that it follows some specific parameters. So it solves a lot of problems from an OEM perspective. So we have some more questions here.
Yeah, I see from Carl Tang, another great question, and I think this is a very interesting one. And this goes into the granularity of SDP, right? So what is the granularity of SDP? What is the operational model of SDP considering the mentioned complexity of connected vehicle ecosystems?
Yeah.
So how granular can you get?
So actually, the great thing about SDP is actually it allows for both very granular provisioning as well as global connectivity. It does both. So an example, it could set up a connection between a batch of ECUs or subsystems with a cloud. So an example of that might be the OEM itself might say, hey, here's all of my systems, I just want to monitor them. Or it can go very granular. It can actually go to a specific process, a specific EXE, and saying only data coming out of that process will go to a specific cloud. So SDP supports IP-based routing, process-based routing, URL-based routing. So through the combination of those three, basically provides the OEM with I can think of it as a toolkit, right? You don't want to use all of these all the time, but you might want to use a V6 address for one specific process. Someone else, you might want to use a URL. Maybe it's a infotainment app. Somebody else, you might be using IP4 address, right? And the key is all of these are happening simultaneously. And that's important because autonomous vehicles, as we've discussed, are going to be in a state of innovation and change. And different partners and processes are just going to be different. For example, high-definition cameras on a vehicle probably are going to use V6 addressing to resolve to the video codec, right? Versus something that helps you find restaurants might use URLs. And we don't want to force the V6 guys to adopt URLs. We don't want the URL guys to go the other direction. That's going to create confusion. What we'd like to do is to let everybody operate how they best want to operate, but now keep them all separate from a security perspective. So we don't want traffic flows from one routing into the other one at all.
And you talked about that it's a software construct. So, maybe it will be good to talk about in a virtualized environment where you have multiple domains and different operating system, different application, maybe different IP scheming. One may be going to V4, one may be going to V6, or maybe including V6 going through V4. Application is V6. What role can SDP play, and should SDP be in each of the domains separately, or how do you see that in vehicle?
So in the vehicle
with virtualization, right?
Yeah. So in the slides, I showed an SDP gateway in the cloud, but you could also have an SDP gateway in the vehicle, because one of the challenges of connected cars and autonomous driving is actually bi-directional connectivity. So you have traffic going the opposite direction, right? So you can certainly the new cars are actually rolling data centers. So you can have as much complexity in the vehicle as you do in the cloud. In fact, it's a concentration because, so you could deploy SDP gateways in the vehicle to handle inbound traffic from the cloud. So that's very important from an access perspective. But the other important aspect of SDP gateways, and we didn't touch into it, is they also have a NAT capability, right? So they can actually bind V4 to V4, V4 to V6, and V6 to V4. And I think that is going to be critical. You can, for example, see where you might have V6 within the vehicle, but for whatever reason, the connectivity is V4 based, and you have to do a 6 to 4 NAT binding, and you could use the SDP gateway in the vehicle to handle that kind of functionality.
What if you don't want to do NAT binding? Because it takes away from end-to-end authentication and mutual encryption. So what do you want to do at tunneling? a V6 into V4?
Yeah, so actually that's a great question. So one of the benefits of SDP's layer 4 encryption, which is application layer encryption, is you can actually do application encryption across a NAT binding. This actually is not possible in the layer 3 IPsec. IPsec, the encryption and the connection are tightly bound. Here, the application rides over the connection. So one of the interesting things is we can actually do end-to-end with SDP, even though the underlying address changes. So that's actually a very nice feature, not only to deal with the complexity, but actually to deal with mobility. You could see a vehicle as it's driving, say on a long drive, it's moving from one service provider domain to another service, and as the underlying addresses is changing, say on LTE, that the application layer encryption is maintained. So I think SDP is a great way to enable end-to-end,
right?
Irrespective of the underlying protocol.
Fantastic. Let me see. Folks, if you have more questions, please text. There's a live chat, so we have another 4 minutes. So I want to talk about this role of the government. I know we briefly touched upon it. The U.S. House of Representatives have passed the AV Start Act,
yeah.
and then the Senate has done as well. What's the role of government in this? And we have not seen a regulation in the enterprise security or in a financial security as to why do you think the government is playing a key role in regulating connected and autonomous vehicle security?
So I think there's a simple reason. While financial security is important, there's no loss of life risk. Just because people can take your money and then the FBI will chase the people and try to get your money back. But if you have an accident, it's very serious. Moreover, with the potential threat of terrorism, I think the U.S. government correctly is saying they just want to make sure this doesn't happen. So you've been seeing a lot of briefings by law enforcement directly with the automotive industry. And I think now the automotive industry needs to react and be proactive. This actually is kind of uncharted territory both for the U.S. government and automotive. Typically, the automotive world is very compliance-based. There's a set of regulations, you follow them, and as long as you follow them, you're okay. Autonomous vehicles and connected cars are just so new, and the development cycle is just so long. I think the automotive industry actually has to be proactive and basically solve these problems ahead of government regulation. What you don't want to do is have these cars rolling and then people say, oh, there's a risk, implement higher levels of standard, and then people are saying, well, we have to reflash the car or we have to bring it back. I mean, that's going to be a non-starter. So I think the great model, if I was to use one, in terms of what the automotive industry does right is, using a simple example, is crash testing. Car companies work above the standard when it comes to crash testing because they want the driver to feel safe in their car. So they don't meet the minimum. They go for the 5-star rating. And they think of crash testing deep early in the design process. How's the car going to behave if it crashes, this or that. They need to take that same level of intensity with cybersecurity. So it's not about just meeting the government mandate, which I think is important. It's exceeding it so people feel completely comfortable getting into the car. Now, using the crash testing example, it's not that cars don't crash, but so much effort has gone into making them safe that when they do crash, they feel like they're not pursuing the automotive industry. So we need to achieve that.
So basically what you're saying is that security has to be foundational in every product development. It's not an added feature.
That's right.
It's not an afterthought. It's not a system level. Every sub-component is to think about the security itself.
That's right. We need to think about the chip, the secure enclave in the chip, the cryptographic library, the processes, making sure the processes boot cleanly, have not been tampered. We need to think about the cloud processes, make sure that the cloud processes are locked down. Then we create a secure connection between the trusted process in the car to the cloud. It requires us to think about these issues now and design security into it. I think waiting for government regulation is not the correct thing because it's not going to help us.
All right, Junaid, it's 9 a.m. here in Pacific in Cupertino, California. I have so many other questions, whether we need a cybercrime unit and so on, but and many more, whether the educational system is there and are we hiring enough and spending enough time, the role of AI and all those sort of things. But I mean, I think that is a if people have more questions, let them send us. We can probably have a follow-up webinar very specific to the next set of questions. One was around blockchain, we saw.
Yes. Yeah.
So maybe there are something about that. Just for the audience, thank you for attending. There are upcoming webinars. One that is next week, which is securing the software-defined car using AI and OTA update, and thereafter we have the last for this year. The last webinar is on 5th of December, which is around saving lives using AI and context-based automotive OTA updates. So I look forward to all of you joining me in the next webinar. And also all the participants and all the great questions for attending this session. Thank you.
Thanks.
Have a great day.